Welcome everybody to session 2. This might be by far the most painful session of the cohort because we have to cover the entire transformer without falling down too many rabbit holes. So let's go ahead and get into it and do our little intro to each session that you'll come to hopefully know and love. As you know, we're on a mission to create the world's leading community for people that want to build, ship, and share production LLM applications. All right, so let's get into it today. We're gonna cover essentially module 1, and we're not gonna get all the way through it yet. We're gonna talk about the transformer paper today, and then we're gonna talk about attention on Thursday. So today, let's be really clear that we wanna understand the high level, and then we wanna understand each of the component pieces. Now, there are going to be an unfathomable number of trailheads as we go here, and we're going to do our best to cover them. This is probably our 5th or 6th shot on goal here, so let us know what you think. We want to understand each layer. We want to understand the overall architecture. Then we want to build one from scratch, and it's going to be a lot. So we're going to talk about embeddings and positional encodings. We're going to send you guys off to the first breakout room to do that. Then I'm going to tell you about how we're actually kind of normalizing after each important layer. We're going to talk about feedforward networks and their role, linear projection, and Softmax. And then we're going to have Wiz come in at the end, and in about 20 minutes, he's going to sort of assemble an entire transformer and train it. Heads up, we typically are going to ask Wiz to be at about a 7 out of 10 speed. With the nature of this course and this particular session, he'll probably be at more of an 8 out of 10 speed. Okay, so with those caveats, let's get into it. We talked last time about how you should never do this. I just want to triple down on the fact that, like, you should never do this because this is a lie, okay? Don't say this. This isn't true. This is not a GPT-style transformer. It's not even like the stuff that is actually in use today, really. Also, this is stupid, and I consider this to be a lie, okay? And so, like, we want you guys sort of thinking, like, starting to think, okay, what's going on here? What is it that people don't really understand? What is it that's maybe a little bit contrarian here about what's going on? Here's another thing that is actually, you guessed it, a lie. Okay, so because, I mean, if attention was all you needed, then why would you need all of this other stuff that isn't attention and that we're going to spend this entire class on? Exactly. Right? So we literally don't have time to talk about attention 4 hours into the course. Okay, so let's go back to the abstract. The dominant sequence transduction modules are based on a complex recurrent or convolutional neural network. That includes both an encoder and a decoder. Okay, cool. The transformer. Meet the transformer. All right. And it's good and it generalizes well. So this is the architecture. You can put something in. Je suis étudiant. Output, I'm a student. We did a translation. Look at that. Why would they choose translation for this? We have this part and we have this part. And if we look, this is actually the encoder block as visualized. Let's be careful with our language here. And this is the decoder block as visualized. Now, the encoder, you might say, is focused on sort of understanding the input. It's focused on really, really grokking that input. If we look at a specific word, how is it related to all the other words in the sequence? Remember, sequence transduction models. Decoder is using the understanding from the encoder. You see this little line, boop, right into the middle here, smashes into the middle. We generate one word at a time through this masked attention. Okay. Now, we talked a little bit last time, but let's just do a quick review here. BART. okay? You guys remember what BART stands for? Well, the B stands for bidirectional. The AR stands for autoregressive. Sequence to sequence. Okay, that's starting to be the vibe I get. Generative tasks that require an input, like, oh, translation. Look at that. Je suis étudiant. Okay, BERT. Now, this is the B. What does it stand for? It stands for bidirectional. What does the E stand for? It stands for encoder. R and T is kind of throwaway here. Representations of transformers. Focusing on understanding the input. You want to answer somebody's question, you really got to understand what they asked, right? GPT styled the kingpin. This is the generative way we do AI today. Look at this. They even said a long time ago, this would probably be good for chatbots. Indeed, it is. Now, we can look across these three categories, and we can look at the style, BART style, BERT style, GPT style, encoder decoder stack. That's BART. So it's bidirectional and it's autoregressive because it has an encoder and a decoder. BERT has an encoder and it's bidirectional. GPT has a decoder and it's autoregressive. So BART is kind of, both of them. Let's visualize. BART. BERT. You see I'm cutting this thing off here? This is just BERT. Okay. GPT. Now, from the BART paper, they literally talk about it like this. There's a bidirectional encoder and there's an autoregressive decoder. Okay, bidirectional, I'm looking at both directions when I look at a specific word. We'll come back to this when we talk about attention. Autoregressive, that means that the next value I predict is based on the last value I predicted. It's sort of in time is the way that this terminology came about, looking at time series regression problems. It's the same with words in a sequence, just like data points in time. What you predict next depends on what you looked at last. These aren't particularly complicated ideas. They're just probably overly complicated words. Okay, back to the first sentence of the paper. The dominant sequence transduction models, sequence transduction, are based on complex recurrent or convolutional that use an encoder and decoder. Okay, let's try to decode some language here by assessing what the actual definitions of these words are. So encode is just trying to convert something into like a coded form, right? So we're trying to convert, in this case, text, in this case, a sequence of text. And really, if we talk about GPT models today, often instructions into a particular form. Now, to decode is just to basically convert that encoded representation back to something that looks like what we put in. Now, that's kind of what's happening. So, Wiz, that's kind of what's happening with the encoder decoder stack, right? We're sort of encoding and then we're decoding. I mean, that's kind of where the name came from, right?
Yeah, we do be encoding and then decoding. I mean, that is the idea, right? So it's the same way that you would think about like any kind of task where you have to understand something and then explain it to someone else, right? First, you have to consume the information, figure out how you think about it, right? And then communicate it to someone else or decode how you think about it, right? Into words that someone else can understand. So, of course, with translation, it's easy to draw that line. But for all tasks, we can think of it that way. But we do encode and decode.
Is it something we need to do each time to encode and decode? Like, is it something that we must have this sort of encoder and decoder? And in the case of BART here, we've got the bidirectional encoder and the autoregressive decoder. It seems intuitive that we would want both, right?
We need in all cases to have both. We need in all cases to have both. We don't necessarily need an encoder module or encoder stack, but we need some way to go from representation to words. So no matter what kind of transformer architecture we use, we have the process of encoding information and decoding information. It's just like the specifics on how we do that could vary from explicit encoding stacks to
That's right.
less explicit methods.
So I want to draw everybody's attention to a couple things. I mean, this is called the transformer, right? So like it's doing transformations of things, is one way to sort of think about this. The other thing I want to point out is we have this positional encoding happening down here. Now, we've been talking about the encoder block. You also just used two words. You used module and you used stack. Now I'm using block here, okay? So this is the encoder block, but here's also some encoding. Is positional encoding the type of encoding that you're talking about we need, or not quite all the way?
Not quite all the way.
Okay.
We live in a world where the words are made up, right? So we sometimes use the same word to represent both the specific process and also its own meta process, right? So positional encoding is a kind of encoding, absolutely, but it is not the only form of encoding that we're going to see. In the same way that, thinking about things like embeddings, what are we trying to do, right? We're trying to create a representation of something from something else. Some could say you're encoding information into embedding space, right? There's a lot of there's a lot of overlap in words, but we must have a process by which we take natural language and we transform it into a representation useful for the model. And then we must have a process by which we take that representation internal and useful to the model and transform it back into natural language. So there must occur those two steps. And you'll see the way we achieve this is dramatically different depending on our architecture. But we do achieve it. And that's great.
In the ears, out the mouth, just like talking to people, right? Okay, easy. So we need encoding, we need decoding. Now, so let's go deeper on this paper here. Let's see what it says. It says, the encoder is composed of a stack of n equals 6 identical layers. Each layer has two sublayers. The first is a multi-headed self-attention mechanism, and the second is a simple, position-wise, fully connected feed-forward network. These are mouthfuls. Okay, you see why this is, and we'll come back to another line in here that I won't even point out right now. Okay, encoder, stack, n equals 6 identical layers. Decoder, the decoder is also composed of a stack of n equals 6 identical layers. In addition to the two sublayers in each encoder layer, the decoder inserts a third sublayer. Look, that's the encoder decoder attention. That's the old encoder talking to the decoder, okay? Now, additionally, we talked about this last time, the masking combined with the fact that the output embeddings are offset by one position ensures that the predictions for position I can depend only on the known outputs of positions for less than I. Okay, if you guys are starting to think, oh my God, this is what the whole class is going to be like, kind of, but actually to really understand the language we're using today, it's going to take 3 weeks, okay? It's going to take us to like session 6 or so to really dig into a line like this, to really understand next token prediction. Okay, so don't worry, everybody's feeling a little confused right now. All right, so when we talk about kind of this other language Wiz, this stack versus block versus layer versus module, this is often quite confusing for people. And it's even more confusing today when we talk about it with state-of-the-art models. So when we talk about layers here from this paper, what are we talking about? We're talking about the encoder is composed of a stack of n equals 6 identical layers. What does that mean here? 1, 2, 3, 4? That's not right. What does this mean exactly?
Yes, the old again, when people created this technology, they were very excited about the algorithmic nature of it. They were engineers first, and they were careful planners of language second, which is hilarious looking back on it, given the Transformers' absolutely incredible use case, which is being great at language. But when they wrote the paper, they didn't have the Transformer yet. So layers, we're talking about this whole section, right? This whole dark gray box.
Yeah.
And all things contained therein, which are either modules or layers.
Let's call it the encoder block here. Okay.
That's right. We're able to treat that is a layer, right? So this is the same thing that we see before, right? Or in other software design, right? Where we have like some unit of information, and the unit of information is called, say, like a class, but we can call something built with that unit of information also a class, right? And it's the same idea here, where we have many layers, but we can fold them together and neatly package them and call them a layer, right? And so when we talk about n times this block or n times this layer, this is what we're referring to. This unit, this collection of things repeated n times. Yeah. And that does not come through in the diagram, right? Though it's literally marked on the diagram.
I mean, the diagram is feeling awfully mid right now. So the encoder...
It's feeling pretty mid.
Yeah. I mean, like the encoder is composed of a stack of n equals... So what we're saying here is there's n equals 6 of these blocks.
Yeah, total
which
blocks.
We're calling layers, okay? And the reason that we're calling them layers, we'll talk about this more on Thursday, is because they have one attention layer. And that's really, I mean, that's the whole point of the paper, right? So we can sort of say the layer is the block when we just are counting attention layers. And you'll run into this in practice. This is quite useful to understand. And then the stack would be then 6 of these, 1 block, 2 block, 3 block, 4 block, on and on. Okay.
That feed into each other, right? And this is the important piece, that are connected by an invisible line that doesn't show up in the diagram. Again, right. The diagram is mid.
The diagram is mid, and we'll continue to explore this as we talk more and more about attention, and if it is in fact all you need. Okay, talking about embeddings. Embeddings, we will spend 2 entire classes on, okay? This is your intro in 2 minutes. Where does Apple go? Okay, Apple goes by the cherries and the strawberries and the bananas. Good job, everybody. Okay, so where does cow go here? Is it at A? Is it at C? Is it at B? A, wrong, C. Okay, crushing it. You guys are crushing it. It's C. And the reason is because puppy is to dog as calf is to cow. And so you might say, here's some age information, here's maybe some size information, but we need more information to be able to represent more things. Like where's attention is all you need on here, right? Where is Sahar on this chart exactly? Where is other stuff? That's not an animal that I can chart on 2 dimensions. The world is complex. We need many dimensions, right? Many thousands of dimensions, typically, with these types of embeddings. Now, going back to the paper. You'll notice from the paper, they say things like, similarly to other sequence transduction models, we used learned embeddings to convert the input tokens and output tokens to vectors. So they need words, they got to turn them into numbers. They use an embedding model. They use a model that's more sophisticated than the one we just looked at. In fact, they use a learned model. Wiz, what do we need to know about learned embeddings and how they're different from regular embeddings?
They are different in that we learn them. And
how do we learn them?
It's just a network, right? As we flow information through our network, as we do our backprop step, we also update our embeddings. So we get better at learning so it's twofold, right? Not only do we get better at understanding what the tokens mean in what context and what position, et cetera, we also get better at actually knowing what a OG vector that token should become, right? So we get better at understanding where to place that original token in embedding space as a start, right? So this is how we're able to learn things like cat, dog, mouse, I don't know, gerbil, whatever pets, you know what I mean? Fluffy pets. This is how we.
The cat is wearing a hat. Yeah, there's all sorts of things we can learn. So basically, we
shove
learn it
them
during
together.
training.
We're not just training. We don't just prescribe what the token is and then say good enough. We also allow the model to gain a deeper understanding of even where that token exists in relation to all other tokens in the vocabulary, right? So that if you imagine our embedding space as a word cloud, which is not unhelpful to imagine it as, right? It's shoving similar words together because they should start in a similar place as they flow through transformer. This is how we get that impressive generalization, right? If cat is close to dog and we say the family owns a pet blank, right? This is how we're more likely to put in something like cat or dog than something like alligator or another animal like a giraffe, unlikely to be a pet, right?
That's right. Unlikely. Yeah. Okay, so learned embeddings. This is also something that is slightly more complicated than regular embeddings. And they go through this whole thing where they decided, hey, we're not going to use learned embeddings because we tried it. Okay, so check that out in the paper. Now, when we talk about encoding, this is after we've done our embedding. So when we create our tokens, which are typically words or subwords, we're going to then create the embeddings. That is going to give us our vectors, maybe 4096 dimensional vectors, let's say. Then we're going to create a positional encoding. Look at this. We're going to encode position within the sub layer of our transformer. Actually, it's not a sub layer. I guess it's a, I don't know if it's a layer. Wiz will tell us in just a minute. We can refer to it as that. What we're doing is we're saying, yo, this word is this close to that word, and this word is this close to that word, and so on. This is just keeping track of the position of words. As they say in the paper, we must inject some information about where tokens are in the sequence. There are many, many choices for positional encodings. Check this out. Learned and fixed. Just as embeddings, we can do learned encodings, or we can do a fixed one. Again, they went with some fixed embeddings here. On this one, there are some nuances there that you don't really need to worry about unless you really want to. To this end, we add positional encodings to the input embeddings at the bottoms of the encoder and decoder stacks. Okay. That's the stuff at the bottom of the stack here. So we're getting the input words, tokens, we're turning them into embeddings or vectors. Then we are doing some positional encoding. We can sort of visualize that like this. This is just all about the order of words. That's really all there is to it. Okay, so what we want to do now is we want to look at this. This is how much of attention is all you need we've covered so far. We're not even inside the encoder block yet. But we're going to go to Wiz to see how to set up embeddings and positional encoding and give you guys some initial code that you can write to start thinking about what's really going on here as we take our words and we get them into a representation that basically locates words relative to one another. It casts us into embedding space. It allows us to now have our numbers that we can feed into this crazy machine we've built called a large language model. Wiz, over to you.
We're going to share this screen. You're going to be looking at this screen. We're going to navigate to the GitHub first, and we're going to navigate to session 2, the transformer. In session 2, the transformer, you can see what we have. We have a note on how we do assignments, just as a clarification to make sure that we're letting you know about the hard mode versus normal mode and what kinds of things are going to appear in assignments and what you have to do to complete assignments in order to get full marks. And then we have our actual assignment. You'll notice that we have the actual assignment here is very straightforward, and the links will be populated here at the top of the page, and those links are going to take you to where you need, like if you want to submit the homework, etc., which is dope. Okay. In the actual assignment, we're going to run these in Colab as a preference. If you have local hardware to do this, that's totally up to you, and you can feel free to do that. But we are going to assume that you're running this in Colab, and so that's what we're going to walk through in class. So there's a lot of text in this notebook. I encourage you to read it. I'm not going to read all of the text as we go through together, but please do feel free to do it. We have a re-explanation of how we do assignments here, and then we start with, with the building blocks. We start with this architecture. This is what we're aiming for, right? So you can see we've color-coded it. We've added a bunch of stuff. This is what we're going to build at the end of this notebook, but we're going to start with this layer right here, which is the embedding layer. So the embedding layer is exactly as Greg described. It's where it's our first input into the model, right? So we can't just shove text into the model. We lack the ability to do so. So what we have to do is we have to take text, we have to convert it to numbers, and then even those numbers are relatively useless to the model. We need to change them into vectors. And that's what the embedding process does, right? Is it converts tokens or numeric representations of natural language into embedding vectors, which are big, long lists of numbers, right? If you forgot what vectors are, there you go, big, long lists of numbers. The way we implement this is way easier than it is to describe, right? Which is that we simply use, we extend the PyTorch module class to create input embeddings, and then we give it this information. We give it a vocab size, we give it a dimension or a D model, we give it embedding layer, and then we give it this verbose flag if we need it for fun. And then we define a forward pass. So we're going to use this language like a lot of times throughout our time together. We are talking about a forward pass and a backward pass. A forward pass is when we're flowing the information forward through the network, and the backward pass is when we're updating stuff based on whatever resultant losses we should get, depending on what we're trying to train for. In this case, our backward pass is going to be handled by our embedding model or layer directly, but our forward pass, we are going to modify it or take it over, right? Because the module has one by default, but we're going to define it, and we're going to define it as the embeddings of whatever input. So forward takes two parameters, self and x. X is the input to this layer. So we're going to take the embedding of this layer with the square root of our model dimension. This is just something they did in the paper because they found it worked good. There's no additional learnings to derive here. That's just what it is. They found this worked better if they scaled their embeddings, and so we too scale our embeddings. Thanks. Attention is all you need. This is the only reason we're doing this kind of forward definition is because we want to be able to scale, and that's that. Okay, there's a question here that you will have to answer, which is given a certain batch size and a sequence length, what the output shape of the input embeddings layer will be, and then we have just a way to test what the layer is working, and you should get a check mark if you're doing this in the pre-written notebook, and you should aim to get a check mark if you're doing this in the self-coded notebook. Okay, so now we've converted a number or a sequence of numbers into a bunch of embedding vectors, sorry. Great, okay. Next step, we want to add information about where those are in the sequence, right? So where the token is in a sequence of tokens is important to describe to the model so that it can help us understand, that, cat, the cat is in the house is a valid language, house cat in the, not valid language, right? So we're both want to describe what words and also where words, right? And how those two are interlinked. Okay, so again, to describe this would take a year, right? Deeply, but to implement code, really easy. So what we do is we use a function. So this is just math happening, right? There's no like there's a lot of code here, but it's all just doing math. Where we're going to use this sinusoidal function in order to assign different values to each position in a sequence. One of the things you're going to notice is that there's no .rand here. There's no, the same values are applied every time depending on the sequence, right? So if we have a sequence of 5, we're always doing the same thing. Every sequence of 5, right? Every sequence of 4096, same. We're just doing math, nice and easy. We're going to use things like this register buffer to make it less slow, but that's the only reason. And this is where the actual math happens, right? We have this original function, and then we just either take the sine or cos of it, and we apply them alternatingly to the indices. So what this means is that at each index that is even, in each index that is even, we're going to apply the cos. At each index that is odd, we're going to apply the sine. So that is the first, second, third element. It's confusing a little bit because zero indexing, but that's okay. That's it. And then we define a forward pass, and you'll notice that we take this input x. This is going to be true of every layer, block, module, right? We're going to take this x, and our x is going to just have the positional embeddings added to it, right? Or in this case, concatenated. We're just going to do this element-wise addition. That's it. There is no trick here, right? And the input to this is going to be our embeddings. We can tell because we go from embeddings to positional encoding. So that's it, right? We just take our embeddings and then we insert this information into our embeddings. You have another question, which is going to be talking about the shapes. We're going to be talking about shapes a lot. If you're not used to tensors with shapes, you're going to become very familiar with them very quickly. A lot of the time when we're troubleshooting issues, when we're dealing with models, we care deeply about the shape of our of the information that flows through our network. And then, of course, we have this test, which is, again, you're just going to get a check mark if you're running this cell in the pre-written notebook, and you're going to aim for a check mark if you're writing it yourself. But that's it, right? So this is the, again, conceptually, these things quite a lot of depth. In the code, easy, right? It's a function. We write code to implement the function. And then every time we see the input, we just add the information that we get from that function to our elements. Boom, there you go. That's it, right? So thank you to PyTorch, which is the backend for everything, which is making this very easy for us. If you want to learn more about PyTorch, please do. We're not going to spend more on PyTorch than saying it's great, and it powers quite a lot of what you see everywhere you see quote unquote AI or LLMs. All right, with that, we'll bounce back to Greg.
We are tokenizing words. We're chopping them up. We're turning the words into numbers. We're embedding the words. We're creating embedding representations. And then we're doing positional encoding. This is all steps prior to actually going into the LLM and actually paying attention to anything. So this means that it was a great question in the chat. Whether we're doing training or inference, this is something that we must do. This is all precursor stuff. And in case you missed it, tokens are not actually words in practice. They're more like subwords, right? They're more like sort of half words. The embeddings that we use in these transformers, they are learned, but the positional encoding is a fixed sine cosine representation. Definitely read about it in the paper. Check it out. Let's talk about add and norm. So we heard earlier that they employ a residual connection around each layer of the two sublayers. This little guy. followed by a layer normalization. So they're doing this little add, boop, and then this norm. What's going on exactly? Well, the residuals, the addition here, these are keeping track of, let's call it the residue of learning, okay? Now imagine you have many layers, aka many blocks in your stack. As you go from one block to the next block, you're going to kind of keep in mind stuff you learned from the previous block just by the nature of flowing the computations through. But what the residuals do are, I like this sort of idea that you want to imagine you just learned something and you're really pumped about it. And you don't want to have to like relearn it later, and you want to share it with other people. You want to share it with the next block. This is what residuals are doing. So we want to pass it forcibly to the next layer, to the next block each time. And that's kind of what we're doing. Again, if we go back, we're sort of grabbing this thing. As soon as we get into the front of the block, we're grabbing it. Boom. Before we go into the attention head, we're grabbing it. Boom. Before we go into the feed forward head, we're grabbing it. Boom. We're just passing through, passing through. Anything we learned in previous blocks, we're keeping the residue of learning alive. And that sort of, compound interest that we get on learning is, obviously pretty important. Now, the layer norm thing, less exciting. It's simply to kind of regularize things and avoid overfitting, because we don't want to overfit more than we want to overfit. In particular, when we're building with LLMs and we're building production LLM applications, sometimes overfitting can be a little bit okay, or sometimes it can be a lot less okay. Here is just a way to sort of generally avoid it. Not that much more to it. When we talk about the feed-forward network, this is sort of the main thing in the transformer besides the masked attention. So let's read about it from the paper. In addition to attention sublayers, again, the attention layer is the main one besides the feed-forward network. We want a fully connected feed-forward network, which is applied to each position separately and identically. So what we're doing here is we're just taking a very simple, the oldest of OGs, multi-layer perceptron type model. And what we're doing is we're sort of taking the inputs and we're kind of pushing them all through this simple feed-forward network. What this does is it gives us, with this simple artificial neural network approach, it gives us a non-linear transformation in our transformation machine, the transformer. It allows us to sort of say, okay, I learned this stuff, I paid attention to this stuff, now let me sort of look at it from a different angle. And let me make sure that that's kind of really something that I actually learned. And so we can kind of think that we need this non-linearity as we go, and it sort of introduces that non-linearity. You can sort of think of it as, Wiz likes to use the example of sort of looking at an orange and then shifting the position in which you're looking at it. Or I like the idea of kind of like shaking the dice a little bit, sort of seeing what you get next. Either way, it's sort of, again, if we go back to kind of what's going on here and add norm, it kind of says, okay, I'm going to take what I learned from the last one and I'm going to make sure that we're normalized, regularized. I'm also going to kind of move it from the way I'm looking at it, shake the dice a little bit in the feed-forward network. And so all of this together, it adds up to actually doing really well on all these great tasks. And, it really does work. We're going to talk about, oh, no, we're not going to talk about attention. We'll see you back on Thursday. We're going to dig in to attention. We're going to keep going. We're going to talk about the linear layer and the softmax, because these are really where the rubber hits the road with GPT models. We also use remember this line from earlier, usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. Oh, this is just quite similar to the one we saw earlier. It's not the same. But again, we're seeing this learned linear transformation similar thing that we heard with embeddings and encodings, and Softmax function to convert the decoder output to predicted next token probabilities. Now, there's only one linear layer, okay? And what it does is it produces these beautiful, sweet things called logits. And it is those, my friends, that we use to actually fully decode and actually predict the next token. So this is just a projection. Now, you can visualize this. In fact, you can visualize it similarly to the way we visualized embeddings, because you can look down here at the kind of what's going on at the bottom here. Look at this little LN guy. So look what we've got here. We've got the MLP residual. Oh, well, what does MLP stand for? Multi-layer perceptron, huh? And then we've got the linear layer that then creates what we use down here to actually predict the next token, which we'll talk about in great detail at a later date. But what does it use down here? It uses this SM, it uses this Softmax. Let's get back to the story here. With all the logits in place, we can actually just say, oh, what's the most probable next token? But that's kind of boring, right? You don't always want people to say exactly what you expect them to say next, right? You also don't want them to be totally divergent. So we use soft max probability instead of like the hard max probability. So what we're going to do is we're going to hand it over to Wiz to walk us, to drive us through the rest of this. Now, my friends, we're going to be at about an 8 here. So buckle up. We got to go from embeddings into, let's just sort of just set this up right here. We're going to go into the transformer here. We're going to go into our friend. We're going to go in, and we're going to have to set up the residual connection. We're going to have to build out multi-headed attention. He's going to gloss over that. He's going to actually have to articulate the add and norm layers. He's going to have to build out a feed-forward network. And then he's going to have to do this build of the decoder block after assembling an encoder block. And once he's got the encoder block and the decoder block, he can build encoder and decoder stacks, which he can then linear and softmax at the end. And when he's done, he actually has to train the thing. Wiz, BART-style transformer, over to you.
We're going to be at an 8, folks, but it's going to be fun. We're going to get through it. Okay, we're also going to spend the rest of our time together trying to get a deep understanding of this. So please don't be, don't worry. We gotta rip through this the first time, and then we're gonna slowly build that understanding. Okay, so we've done embeddings, we've done positional encoding. We have so far converted our tokens into vectors, and we have added information about where those tokens were in a sequence to those vectors. We're ready to get into some kind of bookkeeping stuff, which is going to be our add and norm layer. Our add and norm layer is extremely straightforward. We will simply add and normalize our vectors. That's it. That's all it does. It's extremely unimpressive. There are lots of parts of the transformer architecture which are important and groundbreaking and amazing, and there are some things that are there to prevent overfitting. Layer normalization is there to prevent overfitting. If we have overfitting, it's bad. We don't want that, and so we have this normalization step. You'll notice that we have these fun words: epsilon, gamma, beta. We have an additive, a multiplicative constant, which is going to be our gamma and beta, which are going to be learned parameters. And then we have epsilon, which is going to be our don't get too close to 0, right? So you'll notice that we've got this division symbol. This is a question where I'm going to give you a freebie, okay? You'll notice we have this division symbol right here. One of the quirks of the layer norm is that it's going to be super small. Some of these values are going to be super, super small. So small they might be represented as 0, And if you know your math, you know that when we have the words divide and 0 together, we're in for a bad time. Epsilon just keeps us sane by making sure we never get to 0, right? So we want to avoid divide by zeros. That's why we have this epsilon parameter. You see it all over math. It will never leave us. We're always plagued by divided by 0. Okay, so that's all layer norm is doing. It's just a regularization technique. That's it. We test to make sure it works. If you're running the notebook, it will pass. If you're writing your own code, you'll want it to pass. Then we have residuals. So a residual connection is important. So let's look at the diagram for this one, right? This little arrow here is the residual connection. Okay, so notice that we have stuff that comes into our block, and then it goes both to multi-head attention, and it kind of, bypasses it, right? So this is the residual. The reason we do this is we're learning all kinds of cool stuff. Every time we use attention, every time we use our feedforward network, our model is getting better at learning stuff, right? But we would hate to discard or throw away all of these previous learnings. We love to compound those learnings. We love to make sure that every stage of our network is learning a new thing and not just learning the same stuff over and over again. So this is why we have this idea of a residual connection, which is where we just straight up take what was the input and then we add it back to the output, right? That's it. That's all that's happening. Not very fancy, not very fun, but it's really good and it helps the model learn. And so we do it. And this added norm is just going to add the residual and then do normalization. So when we look at our residual connection, you'll see that we have this X as our input, and then we are going to add that to our layer norm. You'll also notice that we're applying this dropout thing. Dropout is something that if you're familiar with deep learning, you'll know what it means. And if you're not, it just means that, again, in order to prevent overfitting, we need to do something. We need to have some kind of regularization. A dropout is a kind of regularization technique whereby we just eliminate stuff we've learned occasionally. We just straight up drop it out, right? We just this helps us to learn more, better things and to prevent overfitting. So that's all that's happening. This is a big ol' regularization technique, and it's to help us learn better. That's what the residual helps us do. And again, the test will pass automatically if you're not writing code, and it should pass if you are. Then we move to our feedforward network. Our feedforward network is, first of all, it's got a fun name, but it's just a MLP. So this is a multi-layer perceptron. If you're used to the OG machine learning terminology, all this means is that it's a dense network with multiple layers. You'll notice a pattern, right? Which is that we go from D model to DFF, and then we have some dropout, and then we go from DFF to D model, right? So that's our linear 1 and our linear 2. So you'll also notice that DFF is 2048. And if you remember from the top of the notebook, our D model is going to be 512. So what this is going to do is it's going to basically blow up our representation and then shrink it back down. That's all that's happening here. So what this helps us do, like the intuition behind a feedforward network is, and this is a belabored example that I've said many times, so sorry to people who've heard it already, but imagine you're looking at an orange, okay? And if you're looking at the orange from the front, every time, just dead on, right? Every time you try to learn something new about the orange, you're just looking at the same orange dead on from the front, right? The feedforward network helps us move around, right? Look at the orange from different angles, right? So imagine without a feedforward network, there is a worm in the back of the orange, right? We'd never see it. We'd never understand that if we didn't have our feedforward network. Resetting our view, changing our perspective helps us to learn more things. And one of the things that we're going to talk about is that our attention mechanism, our attention heads all want to become experts at different things. If we're looking at we're looking at our data the same way every time, right? They cannot get as much expertise as if we shift our focus. And so that's what the feedforward does. And there's a bunch of words like non-linearity and stuff like that we can over-index on. But the idea is that we're just looking at the sequence from a different perspective. So to implement it, of course, I mean, come on, it's PyTorch. This is MLPs are all this thing does day and night, right? So we create linear layers, and then when we call them, we just chain them into each other, and we have a great day. Okay. Then we test the feed forward again. It will work if you're running the code. If you write the code, it should work. Then we have multi-head attention, which is great. So this is multi-head attention, and then we'll talk more about that on Thursday. But you can imagine the whole attention mechanism happening there in those code cells. Okay. Now we have the building blocks, right? We've got an entity for each of these shaded things, right? We have an add norm, we have a feed forward. We've briefly discussed that there's a multi-head attention that was constructed above. We have our positional codes and embeddings. Now we need to build these blocks up, right? So the way we do that is we just staple them together like Lego blocks, right? So we take our attention block, our feed forward block, and then our residual connections, and then we create a forward pass, which does the thing, right? We take our X and we do this to it, and then we do this to it, right? So what this is going to look like is it's going to look like we pass through our initial residual connection, both the residual and going through the attention block, right? Remember, we go through both of these. Added norm, the input to add norm, right, is the output of multi-head attention and just whatever the input was, right? So our residual connections are going to take the original input X, as well as it's going to determine what the attention scores are, which is done through the attention block. And then we'll do that once more, but this time with the output of this process, and then the output of our feed forward block. That's all that's happening, right? So you can imagine that our little X starts here, and then our X goes through both of these. We add them together, and now our X is coming down here, and it goes through both of these. We add them together. There you go. Easy day. Okay. So that's one encoder block. But remember, the diagram, though it doesn't make this very explicit, is actually 6 of those in a row. And the way that we do that is just by making a stack of them, which is we define how many layers are in our encoder stack, and then for each of them, we apply that encoder block. That's it, right? So again, the intuition behind this, crazy. The implementation is a for loop, so it's not out of this world. We literally just do each one in order, in sequence. Now, when we talk about more efficient implementations, we're going to maybe drop some for loops, and we're going to maybe think about doing this a little bit, more computationally efficiently. But at the end of the day, we're just doing the same thing over and over again, right? We encode, we encode, we encode, we encode, we encode, and then eventually we get the norm out, and we have a good day. So this is going to shock you and surprise you, right? But the decoder is the same thing, except it's on the decoder stack. And we have this really funny little thing called cross attention. So cross attention is going to be information that's shared between our encoder network and our decoder network. Notice this line, right? So we have this regular masked multi-head attention for our decoder. Then we have this multi-head attention, which takes inputs from our encoder stack, right? And so, again, we're going to talk about this more on Thursday, but the idea is that we just have to plumb everything together, and the way that we do it couldn't be easier. When we have our forward pass, we include the encoder output, and then we inject it for every cross-attention block. There you go, right? And again, our actual forward pass through a decoder block is going to have X enter here. We're going to use the residual plus the scores generated through passing through the mass multi-head attention. We're going to go through the next step together, and then we're going to go for our final feed forward. So where our encoder had 2 of these residual add sections, right? This decoder block has 3. And you'll see that represented by the 3 lines in our forward pass, right? X is the same in every one because we just keep reusing it, right? The input of one layer becomes the output of one layer becomes the input of the next layer, and over again. Again, we test it. The test will pass if you're running the notebook. If you're writing the code, I believe I'm not making you write this code, so that'll be easy. And then for the stack, to no one's surprise, We put in a for loop and we run it n number of times. That's it. Finally, we have like, this is, okay, so all of that was to generate internal representation, right? We've gone through 6 encoder stacks. We've gone through 6 decoder stacks, or blocks, sorry. Now what do? We need to get back to vocab. We need to get back to tokens, right? Right now we've got this 512 long vector, which represents scores and all this other stuff, but it's not actually useful to us, right? It doesn't mean anything because what we want is English, right? We want English tokens, and the way we get those tokens is through this final linear projection layer. And this is what's going to produce logits, right? You're going to hear the word logits a lot. If you call them logits, I'm very sorry. I'm going to call it logits the whole time. So that's you're just going to have to bear with me on that one. But this is the idea that we have to have scores for each token in order to determine which should be the next token, right? These are next token prediction machines, or in this case, it's ever so slightly different because actually what we're going to predict is something a little bit more complex, but we're going to twist it back to what we want it to be at the end of the day anyway. So it's all good. Don't worry too much about it. But again, all we're doing is projecting from our internal representation to our vocabulary. Every single token in our vocabulary is going to be possible, right? And so we are going to project into a vector of length our vocabulary. And that's it. Very, very fun, very cool. All right, so finally, we've got all this stuff. We can build the transformer in code. All of that code above gets boiled down to this, which is a transformer module, right? Where we have encode, then decode, and finally project. We set up our encoder and decoder. We set up our embeddings, our target embeddings, our source positions, our target positions, and our projection layer. That's it. And then we go to building our transformer. Unsurprisingly, it's just setting these things up. And then notice that this just says encoder, decoder, right? But there's actually going to be entire lists of encoder blocks that are passed in there. And that's it. This whole, the whole notebook leads up to just this box of code where we return the transformer, right? So just to more explicitly walk through it, we have input embeddings and target embeddings. In the diagram, this is delineated for you. Same with input position and target position. We build a list of encoder blocks, each of them with self-attention, feed forward, and then we create the block, and then we make n copies of them. We do the same thing for decoder, and then we do the same thing for we create the stack, which is what we defined above, which has that for loop, and then we just create our linear projection, and then we init all of them with Xavier uniform distribution, because that's the one that people choose. There's all kinds of papers you can read that needle into the best initialization for each of these layers, and there are correct answers, but you're going to see this Xavier a lot. Okay, so that's all just to build the transformer, and now we have to talk about how we train the transformer, and we don't have the most time. The most important piece of information is this data set creation piece. So if you want to really, really fundamentally understand what's happening, please spend lots of time looking at this cell. We're gonna breeze through it and say that this is setting up the data. So for the training process, we're training on a very, very simple objective. What is the next token? What should the next token be, right? And we want to make predictions that are close to as close to correct as possible based on our training distribution. That's it. That's all we do over and over again, right? We try to predict the next token, and we compute some loss if we are close to or we are further from. That's it. Okay, now tokenization. We're going to talk more later. We're going to talk more later about tokenization. Don't worry about it too much. This is just a helper function to make things easier for you. A get model, same thing. Helper function makes things easier. Get weight, easier. Latest wave file, easier. Finally, we have the training loop. The training loop is the least complicated part of this whole process. The training loop is just a big loop per so we have a number of epochs, right? say, for instance, the example of the notebook is going to be 8 epochs. For each epoch, we will iterate through batches. We will get some stuff that we want to compute, and then we will have our model do that. Then we will calculate some loss. Then we will do a backward step, a backprop step based on that loss. And then we will handle our optimizer so it doesn't lose its mind and get out of control. That's it. So we have some kind of inputs and outputs. We let the model rip on those inputs and outputs. And then we calculate loss based on the inputs and outputs. And that's it. Period. We just do that over and over again until the model learns how to translate English to Italian. You'll see here that the training took about was 30 minutes or whatever on the A100 Colab instance. And then finally, we can do some next token prediction. We load our model, and you'll see this really beautiful. I'm gonna make Greg a little bit sad with me by spending a little bit of time here just to go through. This is what we've done. This is what we've built. The whole notebook. This is what we're left with, right? We have our encoder stack, which has layers, module list, which has 0 to 5, 6, right? 6 encoder blocks. Each encoder block has that attention block, the feed forward block, and the residual connections, which contain our layer norm, right? And then we have the same thing for our decoder, right? So our decoder stack, which has layers, module list, where there is 6 decoder blocks in a row, right? So this whole thing is the transformer, right? Maybe you don't love this representation of it, but that's what it is exactly, right? And so this is what we've built above. And then finally, we end with our projection layer. Our projection layer, again, gets us to our vocab. And you'll notice that the output features in this projection layer are 22,463. You might notice that that's exactly what our vocabulary is, right? So that's not by coincidence that number is that. Okay, so this is what we've done. Very cool. And then finally, we can get it to do the thing. The weather is beautiful today. How are you? This means the day is good or really good or something. And this is how are you in extremely formal Italian. While you're playing with the translation of this, please keep in mind that the model was trained on a very small set of data for very little amount of time and only knows exactly what's in its vocabulary and nothing else at all. So we're going to talk about how to fix problems like that going forward. But for right now, that's fine. This is a big notebook, guys. There's a lot of stuff in the notebook. Please don't think that you have to fully grok every line tonight, right? This is going to be available for the rest of the cohort, the rest of the time we spend together. Each of these is going to make more and more sense as we progress through the course together. But this is kind of like the very zoomed out, very high level overview of Transformer that gets us this. And we're going to see diagrams like this or outputs like this more technically a lot as we move through the rest of the course together. Okay, that is it.
What did we learn today? Well, we learned about the transformer. There's a lot of stuff going on. And really, attention is not all you need. We need all this stuff. All this stuff. Tokens, embeddings, positional encodings, residuals, layer norms, feed-forward networks, linear projection. We need softmax. We need to encode and decode. We need layers, blocks, and stacks. And after we build it, we must train. There's a lot that goes into this.